geometry or an algebra 2 class. I'm then going to discuss the definitions of the trigonometric functions. We're going to practice evaluating trig functions at special angles, and then we will discuss the unit circle. In geometry, you learned about right triangles. So here I have two right triangles. Now I have not put a square in the corner, but sometimes you might recall there being that to denote that it is a right triangle. I have labeled a couple angles here. So this triangle, both of these angles are 45 degrees, meaning that the two legs are the exact same, must be the exact same length as well. The hypotenuse is the side that this side across from the 90-degree angle. So here the hypotenuse would be this side. Notice the hypotenuse of a right triangle will be its longest side. This is a special right triangle because it's a 45, 45, 90. Another special right triangle is a 30, 60, 90 degree triangle. If I were to tell you a few lengths of sides here, so suppose that this were half of a square that had a unit square, so each side was length 1, I would like you to find the hypotenuse. You might think of the Pythagorean theorem right here, and that would be exactly right. So what I'd like you to do is actually take a moment and solve for the hypotenuse using the Pythagorean theorem. Now before you pause the video, I'm going to have you do that on this other one too. Now this is a little harder to show to you right now, but for a 30, 60, 90, this would be half of a rectangle again, where I'm going to assume that the shortest side here is 1, so the side across from 30 degrees is 1. Some students would say or think that because the angle 60 degrees is 2 times 30 degrees, then the side would be double the side across from 30, but that's incorrect. So I actually want you to solve for that missing side. The hypotenuse is actually the side that will be double the side. So in a 30, 60, 90, the little leg is always half of the length of the hypotenuse. That's actually a property that you could use. What I want you to do is use the Pythagorean theorem and find the missing sides. Once you have done that, go ahead and replay. So we'll begin where we were discussing the missing side. So hopefully you used the Pythagorean theorem. You might have found that 1 squared plus 1 squared was equal to the missing side squared. So that tells us that 2 is equal to the missing side squared, and you should have gotten that the hypotenuse is the square root of 2. On the second triangle, 1 squared plus something squared. So 1 squared plus maybe x squared is equal to 2 squared, so 4. So 1 squared plus x squared is equal to 4, but the constant's on the same side. You get that x squared is equal to 3, so that x should have been the square root of 3. These measurements, for any 45, 45, 90, you can have similar triangles, and the sides will be similar, the ratios will be consistent. So what I mean by that is if I instead replace those ones with, say, B or A, then I have B, B, whatever these sides are. So if this is 4, 4, this hypotenuse would be 4 times the square root of 2. Or say that B were the square root of 2, then my hypotenuse would be 2. So this relationship always exists for 40, 40, 45, 90. For 30, 60, 90, again, the short side, the short leg, will always be half of the hypotenuse. If the short leg were 3, the hypotenuse would be 6, and this longer leg across from the bigger angle would be 2 square roots of 3. I believe I said 3 square roots of 3. So that multiple, whatever A would have been. What we're going to use in a few moments when we talk about the unit circle, because the unit circle is the collection of all of the triangles with hypotenuse 1, is I'm actually going to look at these 45, 45, 90, 30, 60, 90 in the case where the hypotenuse is equal to 1. Well, if I wanted the hypotenuse to be 1 here, then A would need to be 1/2. And so my short side would be 1/2 square root of 3 over 2. If I wanted the hypotenuse to be 1 here, for the B, then I would need B to be 1 over the square root of 2, or sometimes we call that the square root of 2 over 2. So for the 45, 45, 90, I have this ratio, and for the 30, 60, 90, I have this one. We'll actually be using this, and we're going to talk about trig functions now, and after we discuss trig functions, I think you all will be able to evaluate trig functions at special angles, these special angles, 30 degrees, 45 degrees, and 60 degrees. I actually want you to take a moment, write these two triangles down. That's not going to hurt. If you write these down, I'm going to reference them a little bit later, and we're going to use them to fill out a chart. So we want to introduce, we'll discuss are a few trigonometric functions. In algebra and algebra 2, you've discussed functions certainly before. For trig functions, much like we write f of x, f is the name of the function. Trigonometric functions, there are 6 trigonometric functions. We'll start talking about the first main 3. And these functions, again, their name always appears with that independent variable. So sine is a function. The full function name would be S-I-N-E. But sin is what we use as that abbreviation, and it's always sine of something. So you never write sin in a trig class. You write sin of theta. We take sine of an angle. You might put an x here, but what's happening is you're always putting in an angle from an acute, so an acute angle in a right triangle. You take sine of that angle, and what that is equivalent to, so the definition, is the ratio of the opposite side to the hypotenuse. And this is a ratio built with the lengths of the sides of a right triangle. Cosine, the full name C-O-S-I-N-E, but C-O-S is what we use as the abbreviation. Cosine, again, of something, cosine of an angle is equal to the ratio of the adjacent side over the hypotenuse. And tangent is the ratio of the opposite side over the adjacent side. Again, the side opposite of whatever that angle is over the side adjacent to whatever that angle theta is. These only work for right triangles, so keep that in mind. In an Algebra 2 class or a trig class, your teacher may have taught you a way to remember this, SOHCAHTOA. What that stands for is the S from sine, OH, O from opposite, H from hypotenuse, CAH, so SOHCAHTOA. Tangent is opposite over adjacent. It really is like FOIL. It's not a definition in mathematics. It's simply just a helpful tool to help you remember. So SOHCAHTOA is a helpful tool to help you remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. There are certainly many others out there. These are I call these the A-list trig functions. So these are the most popular, and then there are 3 others. These actually come from the reciprocal properties. Cosecant is the reciprocal of sine. So you'll see reciprocal, we flipped the numerator and denominator, so now cosecant is hypotenuse over opposite. Secant is the reciprocal of cosine, so you can see that it is the ratio of hypotenuse over adjacent, and cotangent is the reciprocal of tangent, so now we have adjacent over opposite. So these are actually the reciprocal functions. They're below their reciprocal functions, and I call those like the B-list celebrities. As long as you know these A-list celebrities and you can find the values for those, you can always get the B-list values. So these are the 6 trig functions. I would jot this down, maybe put this on note cards. This will be very important in your trigonometry class. Now that we've discussed special right triangles and we've introduced the 6 trig functions, so we've talked about special angles, 30 degrees, 45 degrees, and 60 degrees, and now I want to discuss the triangles, using the triangles to evaluate each of these trig functions. From the 30, 60, 90, so we're going to start with the 30, 60, 90 triangle. If you locate 30 degrees, we're going to find sine of 30 degrees. So remember from SOHCAHTOA, sine is opposite over hypotenuse. So when you look and you locate 30 degrees on that triangle you drew earlier, or you can rewind this video, on the triangle we drew earlier, when we locate 30 degrees, sine is opposite over hypotenuse, and that gives us that sine is equal to 1/2. From that same triangle, cosine of 30 degrees, so from the same angle, cosine is adjacent over hypotenuse. So from that triangle, the adjacent side, that means next to, The adjacent side value is the square root of 3 over 2, and then we're going to use the hypotenuse, which would give us the square root of 3 over 2 over 1, so just the square root of 3 over 2. Now tangent of 30 degrees will be the side opposite over the adjacent side. The side opposite was 1/2. The side adjacent is the square root of 3 over 2. Actually, these two values right here. So tangent will be the ratio of the 1/2 over the square root of 3 over 2. Now maybe you remember if you have fractions, if you have a fraction divided by another fraction and they have the same denominator, that denominator cancels. So tangent of 30 degrees will be 1 over the square root of 3. 1 over the square root of 3 is absolutely correct. Sometimes we don't like putting square roots in the denominator and leaving it like that. It's just improper. That doesn't mean it's wrong. It's just not a formal notation. So instead of writing 1 over the square root of 3, I've rationalized that and I've written the square root of 3 over 3. Cosecant, remember, is the reciprocal of sine. That means cosecant will just be 1 over whatever your value for sine is. Well, 1 over a fraction is the reciprocal, so we simply flip the numerator and denominator and we have that cosecant of 30 degrees is 2. Secant will be 2 over the square root of 3. If we rationalize that, we get 2 square roots of 3 all divided by 3. Cotangent will be the reciprocal of tangent. Remember that before I rationalized it, this was 1 over the square root of 3, so cotangent is the reciprocal of 1 over the square root of 3, which gives me the square root of 3. These are the 6 trig functions evaluated at 30 degrees. These values simply come from the special right triangles that we discussed earlier, from the 30, 60, 90. Because we were talking about the 30, 60, 90, let's go ahead and discuss 60 degrees evaluated each of these trig functions. We would actually be using the exact same triangle, we're simply turning it to go look at the other side. Therefore, sine of 30 degrees, that was the opposite side over the hypotenuse. Well, now sine will be the side opposite of 60 degrees, which is the square root of 3 over 2, over the hypotenuse 1. You'll notice the values for sine and cosine from 30 degrees to 60 degrees will simply swap, because we are turning the triangle and looking at a different angle in that exact same triangle. Tangent then, because we are looking from 60 degrees, will be opposite over adjacent. It will be the sine value over cosine. Because the 2's cancel, we'll have the square root of 3 over 1, simply the square root of 3. And that will pop back up. Cosecant is the reciprocal of sine. So I have 2 square roots of 3 over 3. Secant is the reciprocal of cosine, so 2. And you'll notice tangent and cotangent, their values have swapped, as similarly with secant and cosecant. So for 30, 60, 90, if you have one of these columns filled, you can actually, that will help you fill this column for 60 degrees because you are simply turning the right triangle. For 45, 90 degree triangle, since the sides were equivalent, when you evaluate sine, you can choose either one of the 45 degree angles. Sine will be opposite over hypotenuse. In any of those right triangles that we were looking at, the special right triangles earlier, you will have that sine of 45 degrees is the square root of 2 over 2. Cosine is also the square root of 2 over 2 because they are the same angle. Tangent will be opposite over adjacent, which will be 1. So tangent of 45 degrees is one of the easiest values. It's always 1. Cosecant will be the reciprocal of sine, so hypotenuse over opposite. 2 over the square root of 2, remember that the square root of 2 over 2 is 1 over the square root of 2. So taking the reciprocal, we simply have the square root of 2. This will be the same for secant. And cotangent is 1 over sine, or tangent, since tangent is opposite over adjacent, cotangent is adjacent over opposite, and we also have 1. Once you understand the 2 special right triangles and you understand the definitions of the trig functions, that should help you evaluate any of the 6 trig functions at 30 degrees, 45 degrees, or 90. Fortunately, in trigonometry courses, we tend to use multiples of these angles. As long as you understand these values, where these values come from, then many of the problems that you see in trigonometry will just relate to these. So before I get there, what we've just discussed is graphing, or we've just discussed evaluating trig functions at 30 degrees, 45 degrees, and 60 degrees. Now, when you draw angles, you can of course have other angles. You can have angles between 30 and 60 degrees, like 52 degrees, and you can have larger angles, such as 172 degrees. To organize our angles, we sometimes draw them in standard form. Drawing them in standard form means that we put the initial side on the positive x-axis, and then we rotate the terminal side counterclockwise around the Cartesian plane. So I have a circle here. We often use a circle here. I'll discuss that in a minute, but we also often use this circle in trigonometry to organize our angles and our triangles. So when we draw these angles, again, these angles that have all appeared were in the first quadrant, but you can certainly have larger angles and you just rotate counterclockwise. Positive angles are rotated counterclockwise, negative angles are rotated clockwise. So if you had 172 degrees, that would appear in quadrant 2. 210 degrees would appear in quadrant 3. 400 degrees, you would go around 360 degrees, since there are 360 degrees in a circle. You would go around 360 degrees and then go a little beyond that to 420. If you had negative 20 degrees, you would go clockwise and you would go down to the fourth quadrant, and this would be where negative 20 degrees would be located. I want to discuss now the unit circle. So what I have again is the Cartesian plane, and the unit circle is simply a collection of all of those special right triangles turned for each quadrant. And so what I mean by that is if we took that 30, 60, 90 special right triangle we were discussing earlier with a hypotenuse of 1, the unit circle has a radius of 1. The unit circle, that means the radius is equal to 1. So what we're doing here is taking all of the triangles and making their hypotenuse. You'll notice all of these triangles, they sit or hang from the x-axis, and the hypotenuse of each of these triangles will be 1. Because of that, the base here, because this is across from the 60-degree angle, so it's the longer side, the base is the square root of 3 over 2, so that's your x value for a point on a unit circle where the triangle hits the circle, and the y value, because that is the side across from 30 degrees, would be 1/2. This is an ordered pair, and we use this actually to represent or to evaluate trig functions. So because I have that unit pair, you'll notice that cosine would have been adjacent over hypotenuse. Adjacent will simply be my x value. So cosine of 30 degrees is actually this x coordinate right here. Sine of 30 degrees is this y coordinate right here, 1/2. When we organize the special right triangles on this unit circle, it actually lists all of our values for cosine, sine, tangent. Since tangent is y over x, opposite over adjacent, so it will always be your y over your x coordinate. Any of the reciprocal functions, so cosecant, secant, and cotangent, can be found from those 3 trig functions. So this unit circle is a very well-known concept in trigonometry that helps us evaluate any of our 6 trig functions at special angles. So those special angles meaning 30, 45, 60, or any multiples. So let me show you what I mean by that. If we turn this and use the 60-degree angle, we call this our reference angle, the angle that's between the x-axis and the terminal side of that triangle, we call the reference angle. So here I've rotated that to be 60 degrees as my reference triangle, and the sides, the values will swap. So now my x value, the short side, will be 1/2, and the y value, the longer side, will be square root of 3 over 2. If we flip this triangle into the second quadrant, the reference angle right here is 60 degrees. But this reference triangle actually represents the angle of, so if you'll notice there are 90 degrees And if we rotate that 30 degrees, this side where the hypotenuse is actually represents the terminal side of the angle 120. So from 0 to 120 degrees, you can use this ordered pair to evaluate cosine and sine. This ordered pair comes from the ordered pair we were just looking at, but simply you'll notice the x value will have to be negative now that we're in quadrant 2. The y value is exactly the same. So this ordered pair helps me evaluate cosine of 120. Cosine of 120 degrees is this x value right here, negative 120. And sine of 120 degrees is the square root of 3 over 2. So hopefully this kind of gives you an idea of how we can use the unit circle to actually evaluate, so we aren't confined to the definition using the ratios of opposite and hypotenuse. We can actually extend this further and use the unit circle for any multiples of 30, 45, 60. And so the unit circle helps us evaluate that. Our new definition that we accept in order to do this is that cosine is always given by the x coordinate, and y always gives you the sine value of the angle. So again, this represents cosine of 120 degrees, and this is sine of 120 degrees. If I take the triangle that we had earlier, 30 degrees, and I rotate that into the second quadrant, the reference angle here is 30 degrees. Since 180 degrees are in a line, 180 minus 30, this reference triangle represents the angle, the values for the angle 150 degrees. Cosine of 150 degrees is negative the square root of 3 over 2, and sine of 150 degrees is 1/2. In the third quadrant, rotating those values, if we look at all the multiples, so 30 degrees, 60 degrees, we'll talk about 90 a little bit later, so 30, 60, adding 30 again would give you 90, add 30 again and that gives you 120, 150, 180, 210 degrees, 240 degrees, 270 degrees, 300, 330 degrees, and 360. Now you'll notice these aren't spaced as identically as they should be because I've hand drawn them in PowerPoint, but each of these points that I have indicated right here should be rotated 30 degrees around the circle. And the ordered pairs, you'll notice that ordered pairs, X and Y coordinates are positive in the first quadrant, X coordinates are negative in the second quadrant, both X and Y's are negative in the third, and only the Y values are negative in the fourth. Now, students often confuse where the 1/2 and the square root of 3 goes. Think about whether X or Y should be bigger. If X should be bigger, then the square root of 3 over 2 should go in that position. If Y is bigger, then the square root of 3 over 2 needs to go in that position. And also keep in mind, always check your work and check your negatives. Points right above each other should have the same X value, and points right across from the unit circle should have the same Y value across left to right. We'll now look at the multiples of 45 degrees. If we take the 45, 90 triangle and we look at the first quadrant, then the ordered pair representing the x value and the y value would be the square root of 2 over 2 and the square root of 2 over 2. If we look at this in the second quadrant, then we get the ordered pair negative square root of 2 and positive square root of 2. Negative square root of 2 over 2 appears for x and y in the third quadrant. And in the fourth quadrant, the x value should be positive, but the y value should be negative. We can also take this time to talk about quadrantal angles. Quadrantal angles, we would not have had a definition if we stuck strictly to sine was opposite over hypotenuse for a right triangle. But if we use the unit circle definitions that cosine is x and sine is y, then the quadrantal angles here appearing at 0 degrees, 90 degrees, 180, and at 270, those will simply be the ordered pairs represented by 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Putting all of this together, we have what is called the unit circle. Now I know I haven't discussed these pies yet, but after our conversation you can see that this circle is simply a list of all of those multiples of 30, 45, 60. So 30 plus 30 is 60, plus 30 is 90, plus 30 is 120, plus 30 is 150, etc. And this goes on around the unit circle for one full period of sine and cosine, so one full cycle of the circle. 1, 0 is the ordered pair at 0 degrees. The ordered pair at 30 degrees, you'll notice the x value is bigger than the y value. Those sides come from the 30, 60, 90 triangle we discussed earlier. The 45, 45, 90 triangle we discussed earlier, the sides will swap for the 60 degrees, and this continues. The x's are negative in quadrant 2, the y's and x's are negative in quadrant 3, and only the y's are negative here in quadrant 4. This unit circle helps us evaluate trig functions at any angle. You're going to practice this in your homework. I'm going to read a few aloud right now. If I ask you to evaluate cosine of 5 pi over 6, I'd like you to pause the video and think about what that value would be. So cosine of 5 pi over 6, you would find 5 pi over 6 on the unit circle. We'll talk about pi's in just a minute, what that means, but cosine of 5 pi over 6, you'll find that angle, and cosine will simply be the x value. If I ask for sine of 150 degrees, sine of 150 degrees would simply be the y value. If I ask you to find sine of 225 degrees. 225 degrees, sine would be the y value, negative square root of 2 over 2. If I ask you to find tangent of 180 degrees, so 180 degrees, tangent is going to be y over x. Now 0 over negative 1 would be 0. 0 over anything is 0. However, what would happen at tangent of 90 degrees? So you'll notice sine and cosine will always exist. You'll always have a value for sine and cosine. They're defined over all real numbers. However, tangent cannot exist when x is equal to 0. Therefore, tangent will never exist at a multiple of 90 degrees or 270 degrees. So when I said multiple, I mean an odd multiple of 90 degrees. Tangent of 90 degrees is undefined, and tangent of 270 degrees is undefined. I want you to practice this on your homework assignment. There's a homework assignment I posted on Google Academy, and you'll continue practicing evaluating trig functions at these special angles. Now, I do need to discuss the pies. So I left that out for a few minutes. Radians are another type of measurement. So degrees represent the angle, a value of an angle, so it's a measurement of an angle of rotation, but radians are simply another measurement. Now radians are most generally used in higher up math classes. It's simply a different type of measurement. Just as you had a protractor with angles on it back in geometry, we could have made a protractor with radians. We say that there are 2 pi radians in a circle. What that means is if you take any circle and you take the circumference, so you measure around the circle, and you measure the radius of the circle, because the circumference 2 pi r divided by the radius is 2 pi radians is what we use to denote the amount of rotation in any circle. It's about 6.28, so about 2 times 3.14, but the actual measurement, so 2 pi. Because there are 360 degrees in a circle and there are 2 pi radians, then we say 360 degrees is equal to 2 pi. You'll notice here I didn't use the word radians as a unit measurement. We are often lazy and we leave that off. If you're a physics major, that will annoy you, perhaps. But in mathematics, radians is understood. So it's an understood measurement, meaning that we often don't note it, but if it doesn't have a unit measurement, then it's understood to be in terms of radians. So what I mean by that is if you see this 2 pi and we're talking about angles, that's understood to be in radians. Because there are 360 degrees and that's equal to 2 pi, then half of a circle is 180 degrees and that is equal to pi. We often use that measurement, the equivalence, as a conversion ratio. So what I mean by that is if you need to change from degrees to radians, just as if you needed to change from centimeters to inches, if you needed to change 2 inches, you probably want to have inches in the numerator and centimeters in the denominator. Here, if I want to change from degrees to radians, I want to divide by 180 degrees. This should be 180 degrees, and I want to multiply it by pi radians. That will cancel degrees and your answer will be in terms of radians. Now sometimes pi will cancel, sometimes it won't, but keep in mind this is the equivalence relation. Pi radians equals 180 degrees. To go from radians to degrees, you want to cancel radians and multiply by degrees. Since 180 degrees is equal to pi radians, then you multiply by the reciprocal in order to cancel radians. Now when you look at the unit circle, you'll notice that since 180 degrees is equal to pi, half of 180 degrees is 90, half of pi is pi over 2. Half of pi over 2 is pi over 4, and that's half of 90. So if you can remember that 45 degrees is pi over 4, it will also help you with the fractions here. So when you look at 180, and that's pi, if you take and you divide 180 by 3, you get 60 degrees. So pi divided by 3 is 60 degrees. 180 divided by 6 is 30 degrees, and that's why pi over 6 is 30 degrees. Students often get those confused, but think about the fact that 1/6 is smaller than 1/3, and so that's why these fractions, I know that they might confuse you, but that's why they are aligned in their correct position. So here is pi over 6. 2 pi over 6 would be 2 times 30, so 60 degrees. 2 over 6 is 1/3. If you add 30 degrees again, you take pi over, this would be, you could think of this as 2/6 plus another 6. That would give you 3/6, which is 1/2. And you can actually continue that around the unit circle, and that helps you count these out. You'll know that notice that pi over 4, any multiple of pi over 4 will be a multiple of 45 degrees. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, which simplifies to 3/2, 7 pi over 4, 8 pi over 4. And looking at pi over 6 again, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. 12 over 6 is 2 pi. So if counting around, that'll help you check your work. If you get to 12/6, that's 2 pi, so you're in the correct position. Alright, you all are going to practice these ideas. So in the assignment, I assigned 2 Khan Academy assignments, and one you use special angles to evaluate trig functions, and you can use this unit circle. Remember that cosine is always the x-coordinate. Cosine, x-coordinate. Sine is always the y-coordinate. Tangent, you use opposite over adjacent, so y over x. So tangent is always y over x. Cosecant is 1 over sine, so you'll take 1 over y. Secant is 1 over x, and cotangent is x over y. These are also labeled in the back of your book, and I'll send you, if I can find one, I'll send you a little trig cheat sheet to help you practice these ideas. So the 2 assignments, one assignment has to do with changing radians to degrees and vice versa. One assignment has to do with using this unit circle to evaluate trig functions. So best of luck.